Okay, first thing I want to go over is the schedule for this week. So the first thing is today we're going to finish up on particle motion. That problem, that example problem that we didn't get a chance to get very far on, but we'll be able to finish that and we'll be able to start product and quotient rule. Tonight you guys have homework, just I think over some power rule problems. And tomorrow we'll finish up what we don't finish today, and we can also begin our quiz review. Your quiz is going to be a summative grade, so it will count in the grade book. It's just a quiz, so it's only going to count half as much as your test, even though all the grades that you see is going to be out of 100 points. Quiz is going to be worth half as much as a test. Wednesday, asynchronous day, so no live classes, no requirement from you on Wednesday. But I am going to do a help session just to go over maybe some of the review worksheets of any previous assignments, or if you have any questions, we can do that. 8:30 to 9:30 a.m. I'll record it. And then on Wednesday, I'm also going to do a help session going over Chapter 1 limits test. So I've been starting to enter in grades in Infinite Campus, but I am still waiting on some students to turn in their tests, just some technical difficulties there. So just, but I should be able to release your test back to you tomorrow so that you can look and see what you missed. And if you have any questions, you can ask me during this time, or you can send me a remind and I can clarify any questions that you may have. So I'll spend this time going over that Chapter 1 limits test. And also I'll be reaching out to those of you who may need to do a recovery. So maybe that'll be a good time for us to go over that as well. So, okay, so that'll be Wednesday. Thursday, we'll do another quiz review. Maybe I'll try to come up with another review worksheet for us to do. And then Friday, your quiz. So it'll cover power rule, PVA, particle motion, product rule, quotient rule. I will have a morning help session, 7:15 to 8:15. But there's not going to be 2.1, so there's no limit definition of a derivative. There's no limit as h approaches 0, the f of x plus h minus f of x, so that's not going to be on the quiz. Okay, any questions about this week? Okay, no questions? Everything's clear for now? This calendar is on my website, so if you just go to the homepage and click on class calendar week 5. Okay. Okay, so we briefly got started with this worksheet problem. Let me highlight what we've gathered so far, and we'll just continue our way through this worksheet. Okay, so a ball is being thrown vertically upwards, and it's going to eventually make its way down to the ground. We started with our height function, position function, and we wanted to just go ahead and find the derivatives because we know that velocity and acceleration will also be involved in this problem. So I just went ahead and got the calculus portion out of the way. So we did power rule for each of these terms. So negative 32t plus 64. And then the acceleration function is just power rule again. So constant, linear becomes a constant, constant goes to 0. So we got the height position, sorry, the height function, velocity function, and the acceleration function. Okay, any questions about how we arrived at velocity and acceleration? For number 2, we decided that we knew that the ball was starting at the top of the building, and before the ball is being thrown, it is at t equals 0. So if I can figure out the height of the ball at 0 seconds, that's also going to correspond to how tall the building is, because that's where the ball is going to begin. All right, it's going to begin at the top of the building at t equals 0, 80 feet above the ground. For number 3, it says, when does the ball reach the maximum height? So we're trying to find time t, right? We see the word when, so that's time related. Maximum height. Maximum height, if we kind of visualize this ball in motion, okay, if we visualize this ball in motion, the maximum height is going to be when the velocity is 0. All right. So if we know that the velocity is 0, right, when the ball is being thrown up into the air, there's going to be a brief moment when the ball is not moving before it's begin its descent towards the ground. So if we know that our velocity is 0, we can use this function to figure out the time, right? Because we can specify any velocity and turn around and ask for the t value, which is what it's asking for us to find. So we can replace v of t with 0. We solve for t, we get 32t equals negative 64. Divide both sides by 32. Oops, sorry. Positive 32 equals 64, sorry. So it's going to take 2 seconds for the ball to reach a velocity of 0, and that velocity is going to correspond with the maximum height. For number 4, it's asking what is the maximum height? So how do you think we can use what we found from 3 to solve for 4?
Plug it into the height formula.
Good, right? The height formula, as long as we know a specific time, we can find the position of the ball at any moment in time. So it's asking for the maximum height, it's asking for position, right? Position of the ball. So h of 2, using our calculator, we get 144 feet. So number 5, it says, how long does it take for the ball to reach the ground? So how long, again, we're asking for time. The moment that it hits the ground. So what information, what's another way to say this? What information is that going to provide us for one of the variables in this problem?
Height equals 0.
Good. Height is 0, right? The ground is a position of 0. So we have to interpret ground as height being 0. So if we can replace our height variable with 0, we can turn around and solve for t, and that's what we're looking for. Okay, so replacing 0 in for the height. This is a factoring problem here. I can take out a GCF of -16. Multiplies to be -5, adds up to be -4. We solve for t, and we get t equals 5, and t equals -1. Right? But the only answer that makes sense is what?
T equals
5.
Yeah, t equals 5, right? Because if we look at our restriction is where t is greater than or equal to 0 seconds. So we're only looking at positive. We're only looking at what happens to the ball after we throw the ball. Anybody know why we're getting that -1? What is it about this problem that's producing a -1? Algebraically, why is there a -1 in our answer?
Would the first 0 be at -1?
Yeah, so basically we're talking about a parabola, right? This path of the ball is following the path of a parabola. So we're only considering what happens from this point forward. And there's actually two x-intercepts, right? One's at 5, the other's at -1, but only the 5 is going to make sense for us. The -1 is outside of our problem, so we're not. So basically, we're looking for x-intercepts, and we're getting 2, but only one of them makes sense for us. Okay, number 6. What's the initial velocity? Initial means starting, so starting is t equals 0. So we want to find the velocity at 0 seconds. So plug 0 in for velocity, we get -32 times 0 plus 64. So initial velocity, the ball is being thrown up into the air at 64 feet per second. Okay, any questions there? I think 7 and 8 are pretty straightforward. Finding the velocity at 1 second, find the velocity at 2 seconds, height at 3 seconds. So we're just taking our t-value and just putting it directly into our appropriate functions, right? Height at 3 seconds. Okay, so logically, these numbers should make sense. All right, well, actually, these numbers all make sense, right? Because initial velocity is 64 feet per second, but we know that the ball is being thrown upwards, so the velocity is going to be slowing down as it reaches its maximum height. So 32 feet per second at 1 second, 32 feet per second, yeah, and then at 2 seconds we have the ball is motionless. And then after 2 seconds, the ball is going to begin falling. So maximum height is 144 feet. 3 seconds in, it's going to keep falling. So 128 feet makes sense, right? Smaller than the maximum height. Okay, number 9. What is the speed when the ball hits the ground? So we know how long it took to hit the ground, right? We gather that information from previous 5 seconds. What is speed related to? What variable is that related to?
Velocity.
Yeah, so let's just focus on velocity, right? Let's find velocity first. And then we can decide how speed can be adapted to get our answer. So let's just find the velocity of the ball at 5 seconds. This is the point of impact. Okay, again, using our calculator, we get negative 96 feet per second. So do we need to make any adjustments if our velocity is negative 96 feet per second and if we want to find the speed?
You have to make it positive, right?
Yeah, just make it positive. If the velocity is already positive, then the speed and velocity will both be the same number. It's only when velocity is negative do we have to make any adjustment with speed. Okay, number 10, pretty straightforward as well. What's the acceleration at 1 second, acceleration at 2 seconds? So we just use the acceleration function. Notice that my acceleration function has no variables. It's just a constant, so it'll stay at that value no matter what the t-value is. Our unit of measure is feet per second or feet per second squared. I think you guys also have 11 through 14, right? This is have a older version of this handout. So let me go over 11 through 14. Put this on a separate sheet here. Okay, so number 11 says find the average velocity in that time interval from 0 to 2 seconds. For 11 through 14, put a star next to these. These are easily misinterpreted and so therefore easily missed. So let me define velocity again. Velocity is the rate of change of position. I'm going to abbreviate here, rate of change. So this is how we define average velocity. Average velocity is the change in position over the change in time. So we're going to take our change in position. We know our time interval from 0 to 2, so let's find the position at 2, find the position at 0, and then divide it by 2 minus 0. Using what we've gathered from previous parts, we know the height of the ball is 144 feet. At 2 seconds, 80 feet at the beginning, and we get 64 over 2. So our average velocity in this time interval is 32 feet per second. So let me ask you this, why do you think so many students miss this problem?
I guess instead of doing like what you did, finding the change in position over change in time, they would find both velocities at each second and average those out?
Yep. So sometimes, if we're taking these words at its literal value, you would think, well, velocity, so I'll take my velocity function. And if I want to find the average of those two velocities, then I'm going to add the two velocities and divide it by 2. Okay. But that's not how we define average velocity, right? Maybe that's how we define average test scores, right? But average velocity is defined as change in position over change in time. So yeah, let me show you, in addition to that, what are some other common ways that students misinterpret. So one way is averaging the two velocities together. That's not how we define it. Or maybe students are thinking that, okay, I know I can't use velocity, so I'll go to acceleration. So they know it's slope related, so they do acceleration of 2 minus, change in acceleration over change in time. But another common one is this, where they know it's slope related, but they see velocity and you just want to use velocity because you see that word, right? So v of 2 minus v of 1 over 2 minus 1. This is also not correct. So I know it seems strange that we're finding average velocity without touching the velocity function, right? It seems strange that we're doing this. We're taking position. We're not involving any velocity when we're finding average velocity, right? So I want to connect this with something that we talked about yesterday, or not yesterday, on Friday as well. And it's the concept of average speed. Right? So let's say you took a trip and I asked you, okay, what is the average speed of the trip that you just took? And let's say that to find average speed, you would just calculate, you would figure out how far you traveled. So let's say you traveled 300 miles on the road trip, and then it took you 5 hours to make that trip. And then you would take those two numbers, and then you would do 300 over 5, and you would say, well, my average speed was 60 miles per hour because it took me 5 hours to complete this 300-mile trip. So look at how we calculated average speed. We took the distance, we took the time, but we didn't use anything about speed, right? We didn't know how fast you were going 2 hours into the trip, 3 hours into the trip. We didn't use that information at all. All we needed was distance and time, and then we calculated average speed, right? We don't need any information about speed to find the average speed, just like over here, right? We don't need any information about average velocity to find velocity. All we need is the position and the time at the starting and end points. Okay, does this make sense? I think a lot of students have questions like, why do we not use velocity? It seems like a strange thing, but right. I mean, this is something that we can relate to. So hopefully this will kind of act as an anchor when you're thinking about finding average velocity. Okay, number 12, find the average acceleration in the time interval from 1 to 2. So how do you think we can define average acceleration using average velocity as a starting point or as a model for us?
Change in velocity over change in time.
Yeah, good. Acceleration is simply the rate of change of velocity, right? Acceleration is the derivative of velocity. So in other words, acceleration is the rate of change or the slope of velocity. So let's just find our velocities at 2 and 1 second. So velocity at 2 seconds is 0. Velocity at 1 second is 32. So notice that we didn't touch velocity at all, but our units of measure is still in terms of velocity, feet per second. We didn't touch acceleration at all, but our units of measure is still in terms of acceleration. So here are the commonly misinterpreted formulas that students would use. They would find the average of two accelerations, or they know there's some slope involved, but they want to hold on to acceleration, so they do change in acceleration over change in time, but that's not how we define average acceleration. Okay, any questions with these? All right, 13. Is the speed increasing or decreasing at t equals 1? So on the first page of this handout, we talked about how increasing and decreasing speed is defined by or determined by looking at the signs of velocity and acceleration. So increasing speed occurs when velocity and acceleration have the same signs. Decreasing speed occurs when velocity and acceleration have opposite signs. So we can use that knowledge to help us gather whether our particle is the ball is increasing or decreasing speed at t equals 1. Let's figure out what the velocity and acceleration at those moments in time. So velocity at 1 second, acceleration at 1 second, so we're going to use both information to help us gather the fact that we have decreasing speed because one's positive and the other's negative. Okay, number 14, is velocity increasing or decreasing at t equals 3? If you look at 13 and 14, look how closely they're worded. Okay. But the way that we interpret it is going to be completely different because speed and velocity are different. Okay. And also, this is not talking about velocity because of this increase and decrease. So if we take this in full here, increasing, decreasing velocity is talking about acceleration, right? This is actually referring to the rate of change of velocity, which is just purely acceleration. So we're just looking at acceleration here. Just acceleration. So what that means is if acceleration is positive, then velocity is going to be increasing. If acceleration is negative, then velocity is going to be decreasing. Okay, so using that logic, where did I write this down here? Yeah, over here. So if acceleration is positive, my velocity is increasing. If acceleration is negative, then velocity is decreasing. So we're just going to gather information from acceleration. We know acceleration at any moment in time, 3 seconds. It's a constant, still that constant, so it's negative acceleration. So because it's negative acceleration, my velocity is decreasing. Why do you think this is easily missed? Or how do you think most students are calculating number 14?
It could just be going on velocity.
Yeah, just going on velocity, right? They look at velocity and they say, well, if I have positive velocity, then it must be velocity increasing. Or if it's negative velocity, it would be velocity decreasing. Now, positive velocity would mean that I have a positive velocity, but it's not increasing velocity. Okay, so that increase kind of changes. It's not the same thing as positive velocity. So that word there is the rate of change of velocity. So this is not describing velocity. I know it's a little cryptic, but that's just something we have to understand. And this will kind of carry us into some of the way that AP exams are kind of worded to see if students really understand what rate of change is, and that if you're putting a rate of change on top of a variable, it is not that variable anymore. It's something else. All right, so I mean, it's understandable why students make this connection, right? But this is not talking about velocity. This is talking about acceleration. Yeah, so this is an easy one that's easy problem for students to get tripped up on. Okay, any questions here? But as you can see, right, these are problems that give students a lot of trouble. All right, so I want to kind of point out all the mistakes in hopes that when you guys take it, that you'll be able to avoid them. Okay, let's look at product rule and quotient rule. This is on the notes for today. Okay, so product rule is a formula used to find the derivatives of products of two or more functions. So we've learned power rule, right? Power rule is where we have individual terms that are either added or subtracted with another term, and those are easier to work with. But let's say we have a function that is more complex, where they're not being added together, they're being multiplied together. So if they're multiplied together, they're connected in ways that are a little bit more involved than just adding two fractions or adding two functions together. Because they're being multiplied, that's going to affect the way that the derivative or the slope formula is calculated. It's not quite as easy as just finding f prime and g prime and multiplying those two together and calling that the slope formula or the derivative. It's a little bit more involved because of that multiplication there. So if I want to find the full derivative or the full slope formula of a graph that has these two characteristics of these two expressions multiplied together, we have to go through this formula. Okay, we still involve each of their derivatives, but then they're going to have to be paired up with the other function in this pattern. So it's going to be f prime times g, so it's going to be the first function's derivative times the second original, plus the first function times the second's derivative. So I left off a prime here. You guys can add in a prime there, g prime. So as an example, let's say we had a function that was defined as this. Right. whatever this graph looks like. Okay, it's going to be a polynomial, but it's going to have some. It's going to be all continuous and curved. Okay, whatever the graph looks like. We're trying to find a slope formula for this, but because of the way that these terms are related to one another, we think of it as two expressions multiplied together. So we have to go through this product rule to find the derivative. So dy dx is just another notation for derivative, d over dx. These are all notations for derivative. Okay, so dy dx I can find. This just means find the derivative of y with respect to my independent variable x. Okay, so that's the notation there. So dy dx, or you can call it y prime. You have a lot of variations of notations for derivatives. I'm just going to arbitrarily call my first expression f, and then arbitrarily call my second expression g. And I'm just going to follow this rule here. I'm going to label what I'm going to put in their place to kind of help us see a little easier. So we're just going to fill in what the rule is asking for us to find. So the first thing we need to find is to find f prime, and f prime is the derivative of what's inside this set of parentheses. So I think we can do power rule for both these terms, right? So what's the derivative of 3x minus 2x squared?
Three minus 4x.
Yeah, power rule, right? So 3x becomes 3. 2x squared becomes minus 4x. And then the second part is the g function. So no changes. We're just going to drag that g function down. Second portion is we go to our f function. So we're just going to take our f function, no changes. It's not asking for a change, just asking for the f function. And now the second part is asking for g prime. So g prime is asking for the derivative of this expression. So what's the derivative of 5 plus 4x?
4.
Just 4, right? 5 is a constant, goes to 0. 4x is a linear, so it becomes 4. Okay, I guess we could clean this up, but I'm not going to ask us to clean this up. This is a fairly involved derivative, and that's something that we're going to see is that our derivative is going to get messier and messier. It's going to become more and more involved, but I don't want us to lose the big picture. The big picture is that our function is some sort of a graph, and the derivative just tells us the steepness of any point on this graph. So if I want to find the slope at x equals 1, I just plug 1 into this derivative, and then whatever number I get back in return is the steepness at that point. So essentially, from now until the end of the semester, this is basically what we're doing. We're just learning more and more slope formulas for more and more complex problems. But the idea is a relatively simple one. We just want to know the steepness. We just want to have some slope formula for however the graph is defined. Okay. All right, so we guess have homework a little bit tonight for with worksheet 2 with power rule. Okay. So have a great day, guys. I'll see you guys tomorrow.
Thank you, Mr. Yang.
See you.
Thank
Have a good
you.
day. Thank
Thank
you.
you.
Good
Bye, Mr. Yang. Thank you.
Bye, Mr. Yang. Have a nice day.
Thank you, you too.
Thank you.
See you guys.
Thanks.